Hello and welcome to this Electrical Principles training video. In this video we're going to continue our research into three-phase electricity, and we're going to hopefully start understanding why it was that in a previous video we could remove the neutral link from a three-phase system and still have the loads powered up. So we're going to get a little bit closer to understanding why that's happening in this video. So in the last video we explained in some detail about the test rig that we've got set up here, so we're not going to go through that again, but we've made one significant change for this video. Instead of having lamps plugged in that we were seeing powered up and illuminated, we've now got three heaters plugged into our three-phase system. Each of those heaters is made by the same manufacturer and they are all 2 kilowatts each. So what that means is we've got three loads that are pretty much exactly the same plugged into our three-phase system. Now to start with, we're just going to measure the current being drawn by one of the heaters, and we're going to check what the current is in the line conductor, and we're going to check what the current is in the neutral. And hopefully from a previous video on how to use clamp meters, we should be able to see what those values are and understand why they're behaving the way they are. So let's do that now. So first of all, I'm going to power up my supply. So you can see here the test rig that we were talking about in a previous video. And now what I'm going to do is I'm going to turn on heater number 1. So this is on phase 1, which we refer to as L1. So if I turn my clamp meter on to measure current, I'm just going to clip it over this lead and measure the current in there. So we're getting about 8.4 amperes there, 8.4 amperes. Now, if I measure the current in the neutral, what would you expect that to be at this point? Let's find out. And there you can see again, it's up to
about 8.2
amperes. So we've got the same current in the neutral as we've got flowing through L1, as we'd expect that to be. Now, just to prove that there's nothing funny going on in this situation, we're going to just double check those values for all three heaters. So I'm going to turn on the L2 connection now and measure what we've got running through our second phase. So again, we've got 8.4, 8.5 amperes. So allowing for the tolerances in the manufacture of the heaters, you can see that we're getting the same current flowing through L2. And once again, we've got the same current flowing through the neutral for that conductor as well. I'll just test L3 as well. So I'm going to turn this heater on and check the current flow through L3. And again, we're getting that 8.3, 8.4 amperes quite nicely. And then measure the neutral current again. And we're getting, again, the same current flowing through the neutral. So we're quite comfortable with that. What we're going to do next is we're going to build up to our understanding of how the current is behaving in the neutral in a couple of stages. So first of all, I'm going to turn two of the heaters on. So I'm going to turn on L1, which is there, and L2, which is there. Now again, just measuring the current through here, we've got 8.4 amps coming from L1. We've got 8.3, 8.4 amps coming from L2. Now what would you expect the neutral to be? Bearing in mind that the neutrals from all three of these sockets all come back through this cable here, through this conductor here. So the neutral current from that heater and from this heater are both flowing through this neutral now. So what would you expect the current to be? Now at this point, we normally get a range of answers from our learners, but the most common one is, well, would you just add them together? So you'd have about 16.7 amps, somewhere around that value, 16.8. So let's measure it and see what we get. Now that's interesting. We're getting 8.2 amperes. So actually we're getting the same current as we had when we just had one heater connected. That seems a little bit strange maybe. Let's make it even stranger. We're now going to turn on the third heater. So now we've got 8.4 amps flowing through L1, as you can see there. We've got 8.4 amps flowing through L2, as you can see there. And we've got the same current flowing through L3, as you can see there. So let's see what the neutral current's going to be. What do you think it will be? Let's find out. And look at that. Now we're getting 0 amps flowing through here. And actually, if I remove that from the neutral conductor, you can see that actually this has a little it's measuring a little bit of current that isn't there at the moment anyway, just because of the precision of this device. So we've got 0.1 amperes. So you can see when I clip that on there, we're actually measuring no current flowing through the neutral. And that is the reason why on a previous video, when we removed the neutral connection, the 3 lamps we had plugged in continued to operate, because actually there is no current flowing through the neutral. In this circumstance, we don't actually need the neutral. But why is that happening? So in order to really understand what's happening inside our neutral conductor and within our 3-phase system, we need to go back to the start of a 3-phase system and look at how 3-phase current is generated. So let's have a look at that next. So to really understand a 3-phase system, we need to go back and look at how 3-phase is generated. If you think about another video that featured on Joe Robinson Training, you'll remember that when we generate AC electricity, we spin a loop of a conductor inside a magnetic field, and that generates an AC waveform if we extract the electricity using what we call slip rings. We've then also in another video looked at a cross-section of such a machine and saw how that cross-section actually related to the AC waveform that was being generated. Now what we could do, instead of just having a single loop inside our generator, we could actually install 3 loops inside there and generate each strand of electricity separately, and that would provide us with an AC waveform. It would look something like this inside the machine, with 3 conductors rotating around inside the magnetic field. However, on very large generators, it's quite difficult to extract the electricity from inside the machine. You need some fairly complex machinery, and it can be quite a challenge to extract very large amounts of current from inside there that we'd need at a power generating station. So instead of spinning conductors around inside a magnetic field, we swap the positions of those 2 elements, so it turns into something that looks a bit like this. So now you can see what we're actually doing is we're spinning the magnetic field around inside the generator, and the conductors are held in place around the outside of the generator, and that makes it a lot easier to extract the electricity from the machine. However, as you can probably tell, if we have a permanent magnet inside a generator, that permanent magnet is going to be spinning around, there's going to be a lot of vibration, a lot of heat, and over time that permanent magnet is going to lose its power. So what we actually do is we use an electromagnet inside our generator, and that electromagnet is powered by a DC supply, and it generates a magnetic field in a very similar way to what a permanent magnet would look like. We then rotate that electromagnet inside the generator exactly the same as we would a permanent magnet, and we extract the electricity from inside there. Now, if you look at the positions of the conductors around the outside of the generator, you can see that they're all separated from each other at a very specific angle. Because we've essentially got a circle which measures 360 degrees for one complete rotation, the conductors are all separated from each other by 120 degrees, and that's a really, really important number, especially when you sit in your exams, because you may well be asked that question: what is the angle that the conductors are separated by inside a 3-phase system? Or possibly, what is the angle of separation between the waveforms in an AC system? And the answer is 120 degrees. Now, if we take the same principle that we applied to generating our AC single-phase supply and turn it to our 3-phase supply, and we map the waveform that's produced, you can see that we generate a waveform that now looks like this. So you can see, instead of just the single AC waveform, we've now got 3 AC waveforms that are all separated from each other by 120 degrees. And that is what the 3-phase supply looks like coming out of the generator, and it's very similar to what it looks like when that enters our supply that we've got in this experiment. Now, as we said during the video, once all of the currents meet together in the neutral of the 3-phase supply, for some reason we end up with 0 amps in there. Well, how can that be? Well, let's just have a look at the 3-phase waveform that we produced. Now, what we could do is view this as being the current waveform, so we'll look at it from that point of view, and we can make it so that each waveform is peaking at 8.4 amps. Now, very Pernickety people who know a lot about this will start to tell me off because I'm not using the RMS value, but this is just to illustrate a point, and we'll explain about RMS in a future video. Now, if we look at any point on that three-phase waveform, you can see that all of the waveforms are peaking at about 8.4 amperes. If we pick any point along those three waveforms and put a line in on them and measure the currents at any moment in time, we get three different values of current in each one of the conductors. However, if we add those three values together, what do we get? Well, you can see that by adding those three values together, we actually end up with 0. And what that means is that at any point along this three-phase waveform, the combined currents, when we add them together, becomes 0 amperes. And that is the reason why when those currents all meet each other in the neutral connection of our system, we end up with 0 amps in the neutral. And actually, if you have what's called a balanced three-phase load, which is what we've kind of simulated in this video, you don't need a neutral in the system. And that's the reason why a lot of motors don't have a neutral connection, because you've got three windings in the motor that are all using the same power, all drawing the same amount of current, and therefore we can connect the other ends of those coils together, and when those currents meet each other, they just cancel each other out, and we don't need a return path for that current. So hopefully this video has shed a little bit of light on the matter of that disconnected neutral that we saw in a previous video, and also helped us to understand how there can be 0 amps running through the neutral when we've got a full load connected. However, it may well have raised a few more questions in your mind. You might be wondering about some things. We need to bear in mind that if we've got a three-phase system like we've got here, if we're only connecting up a single-phase load, such as a heater, a lighting circuit, a socket circuit, something like that, then obviously we must have the neutral connected. Only when we've got a properly balanced load that we know is going to remain balanced, such as the example of a motor, can we get away without a neutral. In this situation, these three heaters would actually all get to heat and start clicking on and off at different times, and that would change the amount of current that's flowing through the neutral, so we still need a neutral in that circumstance. What we need to do now is to start thinking about what happens when our loads are unbalanced all of the time. So in other words, if I had three heaters plugged in here that all had different power ratings, then how would I start to calculate the neutral current in that circumstance? Well, that's going to be covered in future videos, and I'm actually going to show you several different ways that you can calculate that neutral current. I'm going to show you the way that I like. I'm going to show you some of the ways that perhaps are required for you to carry out by your awarding body, depending who you're doing your electrical studies under. So at this point, all that's left to say really is, thank you very much for watching.